Another property of glass we care about is refractive index. It's a little bit of a trickier thing to explain. On a true science level, it has to do with refraction is about the speed of light, the velocity of light in different substances. The velocity of light in a vacuum, the velocity of light in air, the velocity of light in glass, the velocity of light in water. Different substances, the air, the water, the glass, have different refractive indexes. And that means that the light as it passes through has to kind of bend in order to sort of make sure it's changing, it's at the different velocities. So essentially, the physics of understanding what a refractive index are a little bit trickier. But what that means is that light bends as it goes from one substance to another substance because of refractive index. So refracting is sometimes referred to as the bending of light. So light density, refractive index, is going to be the same for a piece of glass no matter what size it is. So it's a property that's now unique to that piece of glass. And not all glass has the same refractive index. They don't change by very much. They're similar, but they are slightly different in refractive index. And because of that, I can now have some optical properties that help me to measure the refractive index. And it will help me characterize a particular piece of glass. Turns out that the crystalline structure of glass is why it's an interesting, it's not really a solid, it's not really a liquid, it's kind of somewhere amorphous. And because of this, it does have this nice property of refractive index. It's also what's kind of makes, glass can be kind of sparkly at times. And so I can get this double refraction pattern that does some interesting properties. So refractive index is going to change with a bunch of things. It's going to change with temperature. So if I anneal a piece of glass, and annealing is when I heat a piece of glass till it melts and then cool it. So if you have a chip on your windshield and somebody, sometimes they have, like, if it's really small, they can put a machine on there, and essentially what they do is they melt it so that the crack goes away and then let it cool down, and it makes a nice structure to it. It'd be like if you had a crushed piece of ice and you didn't want it crushed anymore, you could melt it and then refreeze it. That's what annealing basically is. And annealing, the process, it's changing the structure of the glass, right? So it's actually changing the crystalline structure. And so it actually ends up changing the refractive index of glass. So tempered glass has been processed, it's been heated and cooled a lot to kind of harden it and strengthen it. It's going to have a very different refractive index than non-tempered glass. Also, different kinds of glass. Borosilicate glass has a slightly different refractive index than other ones. So that's going to be this basis of how we can use refractive index to characterize glass. So let me show you some examples of things that aren't glass. So this process is what we see. We're seeing the refractive index. So we see that this pencil looks different out in the air and in the water. So as the light is traveling from the air to the water, it is bending. And because the light is bending and our eye knows that this is one piece of pencil, our eye is confused by this. Because as this bent light is entering our eye from this area, it looks different from the light from the air. Turns out that this is particularly important when we have clear liquids and clear objects. So the way that we see a clear object in a clear liquid, it turns out is related to, even though they're both clear, if they have different refractive indexes, that's how we see it. So, we can see this glass rod in water. I can, and I also see the bending, that double refraction. I'm seeing that kind of bending pattern there. And this is because the light is going from the water through the glass, then through the water again. And each time it changes medium, it has to bend or refract because of the different refractive index. So since water has a different refractive index than this glass, I see the edges. You don't even think of it, right? You see it, but what's really happening is this halo here is due to the refraction when it enters and exits the piece of glass. Turns out, if I put this glass in a liquid that has the same refractive index, the light doesn't bend. Doesn't refract. It goes from the silica, this is glycerin, I think, glycerin through the grass, through the glycerin. It never bends. Because it never bends, our eyes can't see where this is. So it looks like it's disappeared in this. And that's the basis of this method that we call the immersion method. It's also called, so that's the basis of this method that we're going to call the immersion method of measuring glass refractive index. Also, it gets tied in with that name of that halo is called a Beck line or a Becky line. I've heard it called both. I'm not sure the official pronunciation. Okay, so again, here we see a sort of clearer photograph. In this one, I have this piece of glass. And right now, in this substance, I can't even see it because there is no refractive change. Therefore, I don't get what we call a Becky line. The halo, which we refer to as this Becky line, is gone. In this one, this line here, this sort of halo on the edges, is due to that refractive index difference. So I'm going to change the liquid until the piece of glass disappears. And at that point, I know, if I know what the refractive index of the liquid is, I know what the refractive index of the glass is. So the idea is that I have my shards in this particular piece of this substance, this liquid. As I change the liquid, there's a couple of ways we can do it. Can be by changing what's in it, by adding some other substances to it and changing the liquid. It also can be done, there's a bit of a temperature effect, so I can, control temperature changing of it in the professional machines. That's actually what's going on, is they're doing a controlled temperature change of the liquid. I start to see that all of a sudden in this picture, it's disappeared. If I keep going, then the glass shards come back again. So here I have a strong difference. I can see a lot of, the bigger the difference, the more that halo effect is getting lighter. The object disappears, and now it's starting to come back. So the refractive index of this liquid is equal to the refractive index of this particular sample of glass. So that's the concept of this in this immersion method. So here are some specific examples of the type of instrument that does this. Again, it can be very automated, and it's looking at multiple pieces, and it's kind of measuring this until they're obtaining the matches. And at that point, and there's a whole standard method for this, we will probably do a very minor example of this by just kind of putting some glass in different substances until it disappears and get a ballpark measurement. But the official measurement method is much more precise and controlled and automated.